Hello everyone, welcome to Compiler Sutra. Today we are going to dive deep into the understanding LLVM architecture, not just what LLVM is, because most of the people think what LLVM is SAT is just a low-level virtual machine, but LLVM is more than that. It is a compiler. It's a modular compiler infrastructure designed for lifelong optimization. Now, question comes: what does it mean by lifelong optimization? When we run our code, let us suppose when we run our any C code from we have when we convert we have any source code, then first it get from preprocessor we get a .i file, then from there using compiler we get a .s file, then from compiler we need a multiple file during link time, then from there we get an assembly file, and during after assembly file we get an object file, then from here multiple object file combined together to generate one executable. So during all this phase optimization is done, and this type of optimization is called as lifelong program optimization. So just not the optimization happens at compile time, but it happens as multiple stages of the program. That is during compile time, link time, idle time, and runtime also, compile time also, link time. So these all places where optimization happen, we call it as a lifelong optimization. So by the end of this session, you will understand what really happened when you run CLang or any front end which is based on LLVM, how LLVM separate front end, optimizer, and back end, why LLVM is modular instead of monolithic, and why its architecture designed the compiler for today. So let's start it. So before starting the lecture or session, I will, if you don't know what LLVM is, then you can see our first lecture, and I assume that you people have some basic understanding of LLVM. If not, please go and understand, or please go and view our first video on what is LLVM episode 0. So you can just, I have shared the PPT on LinkedIn. I will also attach the link in the description. You can click here and visit the video. Now let's start it. So why architecture matter how it is? When we talk about earlier compiler, let's first discuss how they were designed. If we are talking about earlier compiler, then their compiler used to have a monolithic architecture. The front end, middle end, and back end used to be tightly coupled, and it's very difficult to update it and reuse it. If you see here, when we have a compiler like this in the format of, if it is a monolithic, what does it mean by monolithic? If you are from the software background or from any background, monolithic means from one place. Monolith, it's a mono means one, light means from a single structure. It's a Latin word, so it simply means that in compiler term, when we see monolithic, then it means that the front end, middle end, and back end are in one single component. So this is called as monolithic design. So if you see the difficulties in this design is that it's hard to modify, second hard to retarget, third hard to reuse, and hard to experiment. These are the 4 drawbacks of it. So if here comes the LLVM. So what does LLVM did? LLVM had a separate for design for front end, middle end, and back end, and they took all 3 are linked together with one intermediate representation or IR. This IR is the backbone of the LLVM. So now, if you see, if I want to add any front end related changes, I just need to modify the front end component. If I want to add or modify the middle or the back end, then I have to just reuse the back end or need to modify here. But if I want to change in backend, I don't need to take care about the front end. But earlier design, where there was monolithic design, then it was very difficult to reuse the components. That's how the LLVM has changed the game. So this is why the architecture matter. It decreases the code reusability and other thing. So now let's move to the PPT again. So we came to know that why PPT is not changing. So how the LLVM architecture is? It's a layer optimization. It has different layer for each optimization, and it has separate front end, middle and back end. And then third, we are talking about it is designed for lifelong optimization, and it's built for what purpose? Modularity, scalability, and correctness. So these are the fundamental things of the LLVM design. So now we will discuss about goal of the LLVM framework. We already discussed the goal of the LLVM framework. The goal is very simple. We need to do optimization at each stage. Each stage means what? During compile time, during link time, during install time, during ideal time, and during runtime. So the goal of LLVM framework is to enable sophisticated transformation at compile time, link time, install time, and ideal and runtime. So when I say compile time, what does it mean? We have a source code. We have a source code. This source code get converted into .i file, that is called pre-processed output. Then from this pre-processed output, we get a .s file. So during that time, the actual role of compiler works. So during that time, how much time our compilers or the tool chain spend, we call it as a compile time. So compile time here simply means compile time optimization. During compile time optimization, and from this .s file, we generate an object file, and this object file, we may have multiple object file. We need a multiple object file to generate one executable. So we also do optimization during this time. So during this time, it's called as a link time. So what is link time? Optimization across modular during linking time. And then install time, what does it mean by install time? Optimization tailored to the target machine at install time. So when we are installing the software, then we also try to optimize during that time also. Let us suppose we are running on different hardware, and during installation we can ignore some of the module and we can reuse the different modules. So we can also install that time. Then after that, we have ideal time. What does ideal time mean? When we are deploying our software, so during the deployment, what happened? Let us suppose we are deploying the software and software is busy doing some other case. So background optimization can happen to further improve the program. That is mean by ideal time. And during runtime, which means optimizing the program actually running. The system can notice which part is used frequently and optimize those parts to make them run faster. So let's understand the LLVM flow now. We know that we already discussed LLVM is divided into a modular design where it has separate front end, middle end, and back end. Let's call this front end as FE, middle end as ME, and back end as BE. So what happened? We this front end take .i file which is given from the preprocessor and generate one of the intermediate representation after doing lots of steps which we'll see. So this intermediate representation is neither look like a source code, it won't be as assembly, it is between both of it. So we'll see how the IR look like, but this front end generate one of the IR. So once IR is generated, then this IR is given input to the middle end. This middle end run multiple optimization, which is also called as target independent optimization. So that the type of optimization which is target independent. What I mean here by target here is the hardware target. We don't care about on this target hardware it will run. It will just execute and run on the. It don't care about the hardware. The optimization it does not take care about the hardware where they are going to where they are going to perform the run. It's called as target independent, and it will run same for the all hardware. This type of optimization, such as dead code elimination, loop vectorization, and inlining, etc. type of optimization. So it will generate one of the optimized IR. This optimized IR will be given to the backend. This backend will run target dependent optimization and generate what? Generate one of the machine intermediate representation, which will then later converted into the assembly. So this is the complete flow of the LLVM architecture. Now let's see in the PPT. So what we have? We have a source code. This source code is get given to the front end. Front end is generating LLVM IR. This LLVM IR is generating optimized IR. This optimized IR is given to the backend. This backend generates the assembly, and we get the object file. So here the part such as from source code to LLVM IR is called as front end, and from once we have IR, from IR to getting MIR is called as back middle end, and from MIR to what we are getting target specific loading we are doing such as to generate is called a assembly. So if you see the front end, it's a language layer. So language specific processing happen here. So we'll see in detail what each step, each part is doing, front end, middle end, back end. So the all the things, if you are good in compiler design, so you must be knowing about what front end do. Front end specific things are to generate the LLVM IR. To generate the LLVM IR, front end do what? Parsing, HT generation, then semantic generation, then IR generation. And semantic analysis we will see in much more in compiler section design. Then what does middle end do? It's a target independent optimization. What it does, it SSA transformation, dead code elimination, inlining, loop optimization, and interposer optimization. Then we have a backend code generation. What does this backend code generation say? It's target specific loading, instruction selection, register location, scheduling, and assembly emission. So let's see, before diving into deep, we will see what is one of the thing as verbose output in the compiler. So let's see what is the verbose output in the compiler. So here if you see there is a simple code where what I am doing result is we are doing the square of a and b and storing the result in result variable. So what does result is? Result is equal to a square plus b square and we are storing, and if it is false then we are printing it will never run. So just if you see I will try to compile it, or if I want to try to compile it, then how the things will look like. Let me increase a little bit the screen size. Now you can see the code. So now let's try to run. If I want to see what I will run, I will try the compiler name and binary name. When I will try to run it, it will execute, and when I will try to run binary, I will get as output as 125. But if you just I will change little bit modification in the code, as if we use the integer a equal to 5 and I want to try to store a floating point variable, the compiler immediately will give us a warning that hey, this type of typecasting is not allowed. Yeah, implicit conversion from double. So int convert from 5 to 5. So we are losing here dot 5 precision. So which is not good. So we should store in a float. So this is a warning. So it means that even though if you run the binary, we still get the 125. So this warning is important. But compiler, if you see, is only generating the warning and other thing. So if you want to get more information from the compiler internal, we can use the one of the flag compiler has -v. -v is called as verbose output. What is this called as verbose output? So simply, so when I say using -v, what does it mean? It tells the compiler to show everything it is doing internally. It will explain what verbose mode does, which front end it is invoking, which target architecture is selected, what include path are used, which backend is selected, which assembler and linker are called, what exactly command are executed internally. So this is extremely important because it proves that LLVM is not a black box. We can actually see the full compilation pipeline. Let's see with -verbose what is give output. So here if you see, when I run -verbose, it throws a lot of text which is difficult to read. So and can lost also once terminal will close. So what we will do, we'll redirect into a file as verbose, and everything will be stored inside a verbose. If you want to open the verbose, we can just type which editor you are using, code verbose. So this is the what verbose output have. So let's understand the output. So here if you see, first it is showing the clang which I am using, my target and POSIX. So these three is what it says, showing that the first three things, the still here I am talking about, till this three line what they are showing. So they are showing what clang version is 21.1. Install, how I install it, either I install using what other thing. So that's home rev means I install from rev install. So target is ARM, here Apple Driving 2025, and target architecture is here ARM 64, and operating system here is Mac OS. So it is saying all this thing. So this tells us that thread mode is POSIX. This connect to the architecture. So if you see now, this LD command is very huge. So now if you see how much flag it is using. So here, which is my installation directory and configuration file which I am using. If this is a configuration file, it shows all the compiler command I am using. If you want to see, you can see like this. So it is using from sysroot, which system SDK is calling all the include and other path. This is calling from Mac OS 26.xdk. So now if you see, it has a system configuration and another thing. So if you see, it is invoking -cc1. What does it mean? That this is most important part. Here -cc1 means that the clang front end is being executed. And at this stage, Clang is doing the front-end related work, parsing, then performing semantic, then generating LLVM IR internally, and preparing code for the generation. This is still front-end work, no machine code executed yet. But here, if you see, it is executing for, even though I have just provided the code as text file as hello.c, sorry, which sample.cpp, but still all these flags are being added by the compiler. If you see, understand each flag, you can check from your end and understand each flag what it is doing. So here, if you can see the number of flag it is using, the from where it is calling the internal include file and internal system header files. So if you some header file, if you are missing any header file and other things, so it is not able to locate it. So here, if you can see, right, sample.cpp file which I am able to, which I have passed to the compiler. Now all the things it is going, and this user bin LD. What does it mean? That it is using LD as a linker for linking our binaries. So here this include path, if you see on the top, what does it show? This shows where the compiler searched for the header file. The compiler has searched for the standard libraries and the system header. If you see, there will be one command emit. This emit object flag is very important. What does it shows? That this means that the backend has generated an object file. The frontend had passed this, the optimizer has run, backend has generated the machine code, assembler has produced the object file. After the object file got generated, then it goes to where it throws the compilation time error. Right now, it is showing the compilation time error. So warning, it is getting generated as user bin LD. What does it mean? That the compiler combines object file, links standard libraries, resolves symbols, and produces the final executable as a.out. This is the first stage of the compilation pipeline. So now we have understood it, the verbose output. Now we have understood the verbose output and how it works. So the Clang-CC is what? This is the front end and AST plus IR generation, and OPT passes is the middle end optimization, and LLC and CC1 is the backend generation, and AS and assembly is the assembly file generation, and LDLD is for the linking purpose. So LLVM is not just a black box, it's a layered transformation transform pipeline. Now let's move forward and see how the LLVM flows. We already know that the compile time optimization, link time optimization, runtime, and then re-optimize the bit code is done by the LLVM. So before LLVM, we already discussed, right? The compiler has mixed front-end optimizer, back-end, and every tightly coupled. But after LLVM, we get a see here. We have a source code. From there, we got a front end. From the front end, let us suppose it can be any front end, but I mostly use CLang, and for the C and C++, you can use Rust, C, other things for the Rust compiler, which is or any other LLVM based target. So if any LLVM based coding language you are changing, so it will only change this front end. Other apart from the or pipeline, mostly will remain the same. So we will have a LLVM IR. So after the front end will give us what? LLVM IR. This LLVM IR will be in a SSA form. So what will be the SSA form? We will discuss in later format. Just to think as that every variable is assigned at once. This is called SSA format. Once there, we will have what? Target independent optimization done by the middle end. So from here, the middle end will start executing. So we will have what? Code generation preparation, then instruction selection, then after that, machine intermediate representation will generate it. Once we have a IR, then target dependent optimization will run. This target dependent optimization, we will have register location, machine code generation. Once we have, then we have an object file, then linker, then we will have a executable. So this is the complete flow. So let's see what happened in front end. We have seen that we have a source code. From what actually happened in front end is that So what we have seen that in front end, what is happening from source code, we are getting IR. This is the role of front end. From the source code, we are generating what? IR. So how this IR is getting generated, that's the complete working of the front end. The front end now works in 3 steps. It do lexer is there, then parser is there, then from there AST is generated, then from there AST we generate the IR. This is the complete flow of a front end. And now this again I will divide into 2 parts, front end. Let's again what I will do, I will divide front end into 2 parts. One is from source file we get a .i file, that is pre-processed file. This that .i file then generated into the LLVM IR, and this generation is happening in 3 steps. What? Lexer, then parser, then AST, then IR generation. This is the flow for the. This is the flow for what? This is the flow for front end. So here at each state, if you want to see the pre-processed output, so what does preprocessor do? We can use the flag as -e to see the. So let us suppose if I want to see what does the preprocessor file will give output of this, then we can just simply use, instead of we can use here, give here -e flag. This will give the pre-processed file for it. If you will see here what it is, it has just it has included all the, see I have included IO stream, so it has included IO stream here, and it has included IO stream and just given me one of the this file as .i file. We save this as a .i file or pre-processed file. This is given input to the compiler, and then compiler generate the AST. The compiler will generate this CLang will generate now AST for it. It will take the using, we can see the flag as to see the AST using AST-dump -xclang as the AST. So this is the complete AST. It is a very huge file. If you see why it is very huge, it gives the pre-processed file also. What it gives pre-processed file also, it generates the AST. So if you don't want pre-processed file to be generated or just yours, you can use -c flag as this. So what it is generating? It is generating the AST. So from this AST, we generate what? AST is just an abstract syntax tree. It's a data structure which we will cover later. Just first get a clear idea how everything dots are connected, then we will see each one. Now if I just want to generate the IR, then we can use the flag as emit LLVM. So let's say I want to keep IR name as out.ll. One mistake I did here, I just so here if you see out.ll, it simply you can see, right, you will not able to understand it much because it's neither assembly code, neither your source code. It's just a intermediate format of both. That's why it's called IR. So if you see the code here and the IR of this, let's say it's calling the function main. Let me search for the main. So if you, here is the mode. It is allocating some of the variable on the stack. That's what alloca do. Then if you see this load structure, other call structure is there. So here we are, if you see, if you want to see how this IR works, we will take a next session on it. But just currently understand that what IR is about. So this is how the IR look like. And this is the last one of the file which frontend generated. So once this file is got generated, then front end work is finished. Then this front end is given to middle end to generate the optimized IR. Which you can see, right? So what happened internally? So during .i file, what we see a macro expansion, header inclusion, and conditional compilation. Then it gives output pure C++ test. Then we build a AST over it. So what does AST means here? AST is an abstract syntax tree. It consists of a data structure where expression, statement, control, and templates are there. Then from AST2 we get a LLVM IR. So what does it do? It is all types and implicit casts are there. Then control structures all the format. Then it has generate SSA, then basic block, then LLVM IR. Then from there we get an abstract boundary. So why it's matter? Because multiple language support and hardware things are there which we did not remove these dependencies. Then we need to just to we can have a, if you want to do any modification in the front end, then we can just need to modify the front end. No need to change the back end because we want to do some modification in front end. So key point is that there is no contact point. So similarly, if you see the middle end, which is called as target optimization. So if you see on the terminal I showed you previously was the LLVM IR. So on the LLVM IR, two types of optimization is mostly done. They are called as one analysis of the IR and second is called as transformation. Either we will do two things, right? Either we can modify the IR, or what we can do, or we can see our modification is correct or not. So when we do any types of modification, it means that we are writing in the IR. So when we are writing in the IR, so this type of optimization is called as transformation pass, where we are changing the IR. In modification, either we are removing something or adding the thing. So we call transformation passes. And analysis means, so what transformation we have did, it should be correct, so that we can see how it will behave. So LLVM IR, two types of things are doing, or transformation pass and optimization pass. After that we get an optimized IR. This optimized IR will be target independent. So before transforming our code, what does LLVM gather information on the basis of what I need to transform? Transform here means by modify. So LLVM gather control flow, then dominance tree, then loop transformation, then alias of and data flow information. The second major abstraction here is no hardware specific things we are doing, and we are just doing the pure software related things and nothing related to the hardware. So any target, if it is coming till the optimized IR, all the target behavior will be same, or we can mostly say identical, until and unless there won't be any pragma directive, or in macros there would be definition that say this target will behave differently. So transformation passes. So here for the middle end there is a one tool called as OPT LLVM uses, and for the back end here simply means that what does the middle end has given us? Middle end has given us optimized IR. This optimized IR converted into machine IR. So this machine IR will be same or not same, but similar to how assembly will look like. So this optimized IR will have instruction selection, legalizing and lowering. What now goal is, as you know, right? We have seen the virtual register of LLVM IR were very infinite in numbers, and assembly instructions are limited in numbers. So the main role of the backend is to map those LLVM IR into machine instruction, which is register location does it. This is one of the optimization I told you, and which instruction to select at what time, that was instruction selection do. But they don't perform the optimized IR, they work on the machine IR. So what happens here? Instruction selection, then legalization of the instruction. Now all IR operates are directly supported by hardware, the backend, and the third major abstraction boundary is the compilers knows the target architecture. Instructions are concentrated, register become visible, and schedule constant appear. The register is now target specific. So here if you see the optimized IR is in SSA format, but the machine IR will be no SSA format, and no virtual register will be there, no abstraction instruction. That's the third major boundary. Now the backend second part will be from machine IR to we are generating assembly. So this is the complete flow from machine IR to assembly we are generating. So each type now we have seen. So in the next video we'll see how the LLVM IR look like.